Hello everyone. Uh, Today I'm Rajita from EC third year. Today we are going to discuss about some of the experiments performed in the digital signal processing laboratory. So the aim of the experiment is to study about the performance of various filters like moving average filter and other derivative filters. So first let us look into what is moving average filter. A simple low-pass finite impulse response filter, which is generally used for smoothing of an array of sample data or signal. It generally takes L samples of input at a time and takes the average of those L samples and produces a single output point. So it is like the function is 1 by L into sigma k equal to 0 to L minus 1 x of n minus k. It will be simply taking a window of length L, and it will be taking the average of all the particular window particular signals present in the window, and at each point it will be giving the average of that signals. So as the length of the filter increases, the smoothness of the output increases. But the disadvantage in using this filter is in in high slope points, the data is made increasingly blunt. So this implies that the filter has like excellent time domain response, but a poor frequency domain response. So the main important functions of moving average filter are: first, it takes L inputs and computes the average of those L points and produces a single output. Due to the calculations involved, the filter introduces a definite amount of delay. And this filter acts as a low pass filter but with a poor frequency domain response. So the next is a signal flow diagram of the moving average filter. As we can see here, x of n is the input filter. Here Zn is the time delay which we are giving. So when we are taking the input x of n, so at each time, after each unit delay, we'll be taking the response like B1, B2 and all. And at the end of the system, then we'll be taking the sum of all the inputs that are obtained after every delay. So that is nothing but our y of n. So this is the transfer function of the moving average filter. So as we know, transfer function is calculated by taking the input of the impulse function. So this is obtained by y of z by x of z, where y of z is the output and x of z is the input. So the function is like this: 1 by L into 1 by L into sigma of k equal to 0 to L minus 1 z bar minus k, where L is the window which we are taking. So for observing the performance of this filter, we have done the frequency analysis of the impulse response by considering different values of L in the MATLAB. So as we can see here, the magnitude response is, this is the magnitude response of the various filters. One is first order filter and the second one is 3-point difference, central difference filter. So the blue line here indicates the magnitude response of the first order difference. So this is a plot of amplitude versus frequency. And the red color indicates the 3-point central difference filter that we'll be discussing in the next session. And the second graph shows us the phase response of the first order difference filter. Here that is indicated by the blue line, and the red line shows us the 3-point central difference filter. So moving on to first order derivative filter. As the name indicates, derivative implies the difference of the signal. So first order derivative filter is a Cauchy and LTI filter. So it is Cauchy because it depends on the current input as well as the previous input. And it is LTI because it follows the homogeneity and additivity properties. It is basically used to highlight the high slope regions of the signals. So the equation of the first order derivative filter is like this: y of n equal to x of n minus x of n minus 1. Here x of n minus 1 is the previous input. And the transfer function is obtained like y of z by x of z. This is the impulse response of the input signal. So it is given by 1 minus z inverse. So this is the signal flow diagram for the first order derivative filter. So here x of n is the input which we will be taking, and here we are giving a delay function z inverse, and the output is calculated by adding both the present input as well as the delayed input. Here it is delayed by unit 1. So we call it first order derivative filter. So moving on to 3-point central difference filter. It is a Cauchy as well as LTI because it depends on the previous input and the present input. Here the difference from the before which earlier filter is, here the delay is 2 units. So it is quite more accurate than the first order filter. So the equation for 3-point center difference filter is y of n equal to x of n minus x of n minus 2. Here n minus 2 is the previous input which is delayed by 2 units, and the transfer function is given by 1 minus z inverse. So the signal flow diagram is like this. X of n is the input which we are taking, and it is delayed by z power minus 2. Here minus 2 indicates the 2 units which are delaying, and the output is obtained, y of n is obtained by integrating x of n and x of n minus x of n minus 2. So these are the set of questions which you have to do in the laboratory session. So the first one is choose a filters to smooth out the high frequency noises present in the signal. So as we have discussed earlier, for smoothing the high frequency noises, we will be using the moving average filter. So let us look into the Arduino program, how to do it. So yeah, so here float, first we will be taking samples. We took 1000 samples in this question. So float is the type of variable it indicates. Here since we are taking decimal numbers, we will be taking float, and x of 1000 indicates the number of samples we are taking in an array, and here we are taking y as an output function. So we are initializing the elements of the output to 0, and here we are giving the window L equal to 8 here. So moving on, void setup serial begin 9600. So this 9600 is the baud rate for the function. So going into the loop, here we have written a for loop int I equal to 0, I less than 1000, I plus plus. So we are starting from 0 and we'll go till 1000. I plus plus indicates after completion of every loop we'll be increasing the value of I by 1. So there is inner loop again. We are initializing j equal to I, and it runs till j greater than or equal to I minus L, and j minus minus. Here we will be this inner loop is for running the loop for the L number of tens. Like for suppose if we say if we start with 0, I equal to 0, it runs I from I equal to 0 to I equal to 7. It will be taking the average of all the 7 components. So here y of I is the output signal, y of I equal to y of I plus x of j. X of j is the j is which we are taking the inner loop. So every time the inner loop runs, we will be adding the value of x of j to it. So after the completion of inner loop, we will be going to y of I equal to y of I by L. So this is the average which we are taking, like L is the window. Okay. So after completion of the function, we will be printing the signal. So serial.print x of I, this is the input signal which we are taking. And the second thing which we are denoting by comma, it is used to differentiate between two different signals. The signals are functions. So the next step, serial.print L, y of I plus 350. Y of I is the output signal. Here we are adding 350 in order to differentiate the two x of I and y of I signals. So when we add some constant value to it, so we can shift the value of the signal by the particular value. So this is all about moving average filter. So now we will go to the second question. Choose a filter to emphasize high slope. Let us see the output of this. So this is to upload the function. So and this button is used to verify our code. So after uploading, we have to press. It is taking time for uploading. So after uploading, we'll Control plus Shift plus L gives us the output. So this is the plot of our signal. So blue color indicates the x of I, that is the input signal, and the red color is indicates the output signal. So here we can see the smooth end components of the signal. So this is basically what this one does. So moving on to next one. So choose a filter to emphasize high slope portions in the signal. So it basically, as of we have discussed earlier, this is done by the derivative filter. So let us look into the code of this. So here, as discussed earlier, we will be taking 1000 samples, and we are giving two arrays here, y and yb, and we are initializing them to 0, and the baud rate is 96,000. So first thing is, like, we'll be taking separate function moving average, void moving average, and these are the inputs which we'll be taking. So like this is similar like which we did in the earlier one. We'll be taking I equal to 0 to I plus plus, we'll be initializing them to 0, and then we'll be taking the average y of I equal to I of I plus x of j, and this is after the completion of the inner loop, we'll be taking the average of all the samples by the window L, y of I by L. So this is the derivative filter. So as you can see in the second loop, I equal to 1 to n will be running it, and there y of I equal to y of I minus 1. So this is the first order derivative filter, and the second loop is for 3 central point derivative filter. So here we will be taking y of I minus 2. So this one is this one we are doing for the second order derivative filter. So, and here you can see that serial print y of I is nothing but the moving average filter, and y of I minus 400, that is the first order derivative filter. Here we are decreasing it because so we can see in the lower part of the signal. And the second again we are giving the third 3-point center difference filter, yb of I minus 600. So let us see the plot of this. So the blue color one is the moving average filter, the output obtained after applying the moving average filter, and the red color line indicates the output obtained after the first order derivative filter, and the green color indicates the output obtained after the third order 3.3 central point derivative filter. So we can see that in the derivative filters, the high slope components are attenuated. So this is basically the function of the derivative filters. So moving on, the third question is we have to design a moving average filter with a value of L equal to 0.8 into n to extract the baseline drift component of the signal. So to extract the baseline drift, we have to remove all the low frequency components. First we'll be taking 1000 samples of input, and y and z are the we are initializing them to 0, and then we'll be taking the baud rate 96,000. So basically this loop is for, the first loop is for calculating the moving average. So we'll give x of I as the input, and y of I is the output obtained after taking the moving average. Here we are taking a moving average with window of 8. In the second loop we are taking the moving average with a window of 800. As we have discussed, as the value of the filter increases, it becomes more smoothened. So all the low frequency components can be removed by subtracting z of I from y of I. So we will be running a third loop where y of I where we will be getting output by subtracting the z of I minus from y of I. So when we'll compile this code, it removes all the low frequency components. So here we are printing x of I, that is the original input signal, y of I, that is the final output signal, like after baseline wandering and all, and z of I, that is a signal obtained by taking moving average with a window 800. So this is a plot of the graph. So the red color blue color indicates the x of I, that is nothing but our input. Red color indicates the moving average filter with a window base after removing the baseline wandering, and the green color one indicates the moving average filter with L equal to 800. So this is all about baseline wandering, how to remove the baseline components. So moving on, the next question is find the output of signal processing system which performs derivative filter 2 and then perform moving average filter with an n equal to 8. So here we'll be taking the input x of x, and then we'll be taking y and z as we'll initialize them to 0, and then we'll be taking the baud rate 96,000. So first we have to perform the derivative filter. So y of I equal to, first we'll be taking a loop. So for 1000 times we'll be running the loop x of I minus 1. That means we're subtracting the previous input from the current input. So in the second loop we'll be taking the moving average. So z equal j equal to I to j equal to I minus 8, like for 2 loops will be running, and we'll be taking the average of the entire signal. So j of I equal to j of I by 8. So after this, so from here we are taking the input obtained after the differentiating. So we took y of I, not x of I. So in the then another loop we'll be printing the signal. X of I is the input signal, and y of I is the signal obtained after first order derivative, and z of I is obtained after derivative filter and moving average filter. So we'll plot this. Just Control Shift L. So here x of I is blue color line indicates x of I, and a red color line indicates the center first order derivative filter, and j of I indicates the moving average filter for the first order derivative filter. So that's all with the various types of filters. So today we have seen how way to use different filters and how to write a code for that. So that's it. Thank you.